This time, I'm going to talk about normal inverse Gaussian process in Python. The normal inverse Gaussian process is a type of Lévy process used in probability theory and financial modeling. It is a stochastic process that belongs to the class of generalized hyperbolic distributions and is particularly useful for modeling heavy tails and asymmetric distributions. The normal inverse Gaussian process depends on those four variables. Alpha controls the steepness of the distribution. Beta controls the skewness. Delta is a scale parameter. Mu is a location parameter. All the mathematical formulas in my model came from this paper. So if you are interested in the mathematical detail, you can download this paper and read this paper. The NIG process has independent and stationary increments, and the NIG distribution can model returns over different timescales. The NIG process has an infinite number of small jumps in any finite time interval. The distribution has semi-heavy tails, making it suitable for modeling financial asset returns. The NIG process can be constructed as a Brownian motion subordinated by an inverse Gaussian process. Now, let's compare this normal inverse Gaussian process versus Variance Gamma process. The process type of both processes are quite similar, but in this process we have infinite variation, but in Variance Gamma process we have this finite variation. And for this NIG process we have Brownian motion subordinated by an inverse Gaussian process, while for this Variance Gamma process it has Brownian motion subordinated by a gamma process. For the jump structure, both of them have infinitely many small jumps, but NIG process has rougher paths and Variance Gamma process has smoother paths. For the skewness and kurtosis, both of them can model skewness and heavy tails. And the parameters, of course, they are different. And for the variance growth, it's quite similar. They all have linear in time. In my previous video, I talked about Variance Gamma process. And before that, I had another video I talked about Merton Jump-Diffusion process. If you haven't watched those videos, you're welcome to watch those videos as well. Now, let's compare among those three processes. If I compare NIG process versus VG process, both are infinite activity processes, but NIG has infinite variation, making it better at capturing extreme events. when we compare NIG process versus Merton Jump-Diffusion process, NIG had many small jumps, while Merton's model had finite number of large jumps. When we compare Variance Gamma process versus Merton Jump-Diffusion process, VG has no large jumps, whereas Merton's model explicitly allows for rare large jumps. Now, let's go to Python to check out our model. This is my Python model. First, I'll set all the parameters, and then I will model the first passage time and draw the graph to check out the first passage time distribution. And then we have this characteristic function of normal inverse Gaussian random variable. Again, about this characteristic function I talked about in my previous video. You are welcome to watch that video. And then we have this function for the PDF inversion, and basically it will invert the characteristic function to compute the PDF. And this function will calculate the NIG density, and this function it will evaluate the NIG density using parameters alpha, beta, delta, and mu derived from the internal parameter theta, sigma, kappa, and c. And then we'll plot this NIG histogram. And lastly, we will use this MLE method to estimate those parameters. Okay, now let's run our model. You can see the first graph is the first passage time distribution. And these light blue bars, the histogram, this represents the empirical distribution of first passage times based on simulations or Brownian motion with drifts. And each bar's height shows how frequently a specific first passage time occurred in a simulated data. And you can see the red curve here. This red line represents the theoretical inverse Gaussian distribution, which is the analytical probability density function for first passage time of our Brownian motion with drift. And you can see the histogram closely follows the inverse Gaussian curve, meaning the simulated first passage time matched the expected theoretical distribution. And you can see the peak is here, about 2.5. This suggests most paths reach the barrier at that time. The right skewed shape here indicate that some paths took significantly longer than the mean time to reach the threshold. Now, let's check out this NIG histogram. The light blue bar is the histogram of the simulated NID distributed random variables, and the red line is theoretical NIG density function. And you can see those blue dots. They are density estimation via Fourier inversion. And the histogram, this light blue area, represents the empirical data from multicolor simulation. The red line shows the expected theoretical NIG density calculated using the modified Bessel function. The blue dots represents another method to compute the density via the Fourier inverse formula. The graph is bell-shaped but slightly asymmetric, meaning the distribution has heavy tails and skewness. This is a key characteristic of the NIG process. So, the simulated data, this histogram, closely matches the theoretical NIG density, this red line. And the Fourier inversion method, all those blue dots, aligns well with the red line, validating the density approximation. Now, let's take a look at this QQ plot. This QQ plot compares the quantiles of the sample data set with the theoretical quantile of a normal distribution. This x-axis is the expected quantile from a standard normal distribution. The y-axis is the quantiles from the actual data set. And the blue dots is empirical data points, and the red line is a theoretical normal distribution line. You can see the middle section follows the red line closely, indicating normality in that range. But if you take a look at the tail, this side and this side, you can see the left tail is more curved downward, meaning the sample has more extreme negative values than expected under normality. The red tail also suggests slight asymmetry. So the sample distribution has heavier tails than a normal distribution, which align with NIG properties. The skewness suggests that it's not perfectly centered around zero. This is strong evidence that the underlying distribution differs from normal. Lastly, we use this MLE method, estimated all those parameters. You can see the result is here, and if you compare with our initial parameters, they are quite close. This is how I built my normal inverse Gaussian process in Python. Please comment, like, and subscribe to my YouTube channel. Thank you for watching.